Okay, so we are looking at factoring trinomials that have a coefficient other than 1 on the x squared term, which is the a term. And these are usually in, or they should be if we are factoring, in standard form, which is ax squared plus bx c. And if they're not in that form, we want to transform them into that form if there are 3 terms, making it a trinomial. So this is a way just to factor trinomials. If there are not 3 terms, then you probably shouldn't be doing this method. So for this one, we use the special x method. And what goes on the top is AC, which is the a value, times the c value, which is -12. And on the bottom is the b, which in this case is just 1. The coefficient of x is just 1. Okay, and what our goal is to find numbers that multiply to AC but add to B. So first you're gonna, well, this is negative, but we'll worry about that later. First, you're gonna have to find numbers that multiply to 12 or -12, and out of that list, choose the set that adds to 1. So what we do is we start by making a list of things that multiply to 12. And in this case, the numbers are low, 12 and 1. But if you have numbers like 280 or something like that, the list is just going to be a little bit longer. It's going to take a little bit more work. It's the same process in the end. Just make sure that when you're making your list, you're doing it in order from 1 to until the numbers repeat. Because if you don't do it in order, then you might skip one. And then when you can't find the factor, you don't know which one you skipped. So start from the beginning. We know that factors of 12 are 1 times 12, 2 times 6, 3 times 4. And then once we get to 4, because we already have 4 on the list, I know that I can stop listing factors. So out of those, if I were to add or subtract them, no matter where the signs were, which ones would add or subtract to a positive 1? And what would work is 3 and 4 if we made 3 negative. So we're going to make 3 negative and 4 positive. And this is where you stop and check. Does -3 times +4 equal -12? Yes. And is -3 plus 4 equal to 1? Yes. So this right here is always a multiply, and this one's always a plus, and then the signs are shown on these values. And we always divide these two fractions by a, which in this case is 6, and the variable x. Not squared, just the variable like you see it in the problem. Sometimes I put a box around this to show myself what I'm choosing. So to write the parentheses, we have to simplify these fractions first. And I'm going to erase these factors now. We don't need them anymore. We have to simplify the fractions, and that's what makes X method really good, because in other problems, the way that this simplification is like taking out a GCF like 3 different times. So it's a lot easier to just right now simplify these fractions. We know that 3 goes into 6 twice, and what's left up at the top is a -1. There's no more 3 if we divide both of these by 3, but there is a -1. And then on the bottom, 2x. So just like simplifying fractions, like you know how to simplify them, just make sure that the negatives stay in the same place, the x's stay in the same place. And here we're going to divide these by 2. And we get 2 over 3x. And these fractions mean something because they represent the parentheses that come from the factored form. The bottom plus the top, which in this case is negative, bottom plus the top, bx plus 2. And this is the factored form of 6x squared plus x minus 2. And we can prove this or check our work by foiling this. So this is the answer, and you would leave it just like that. But to check, let's see what that looks like. 2x minus 1, 3x plus 2. So first, 2x times 3x is 6x squared. Outers, 2x times 2, inner, and last. And we notice that we have like terms in here, which gives us a result of 6x squared plus x minus 2, which was the original problem, which tells me that we factored correctly. So this is Miss Silvestri's special x method, and this would work for any type of trinomial as long as it's factorable. So I would give you problems that are always factorable if I'm asking you to factor. Later in our chapter, we will get to problems that are not factorable, and we're going to learn other methods to solve those.